In order to understand how to program a computer, it's very helpful to understand how a computer works and understand how data is stored in a computer. We're working with a small computer here, a microcontroller, but this right here is the computer chip. This is the processor for the Arduino Uno, and it has all of these pins here which connect it to the board. We're going to just take a little bit of a sneak peek into this board and how it actually works. So we're going to come over here and look at these drawings that I've made. We have a resistor here, and denoted by this squiggly line. And if we have a high voltage over here and a low voltage over here, we get current running through from left to right through the resistor, and the voltage drops across the resistor, which means there's a higher voltage here than there is over here, always in a resistor. Voltage always drops across the resistor. The next electrical component to look through is a diode. We have A and B on either side of the diode, and current running through from A to B. And this I represents current. Don't ask me why it's an I, but that's what we use to represent electrical current. We have this symbol for the diode has this arrow on it that indicates the direction of current flow. So here, if the voltage at A is greater than the voltage at B, we see that the current flows through from left to right through the diode. We cannot get the current to flow from right to left through the diode if the voltage at A is less than or equal to the voltage at B. We just don't see any current running through the diode. The next component that we need to look through is the transistor. We have a high voltage here and a low voltage here, and similar to the diode, there's only one direction the current can go through the transistor, from here to here, from the high to low, as denoted by this arrow. But we also have this other pin, which is called the base. And the way this works is voltage will not run through from high to low unless there is also a voltage at the base. So what we do is we add a little bit of voltage here. It takes about 0.7 volts to open up the pathway here through the transistor and allow current to flow. It's a very little current at 0.7 volts, and the current that's allowed through this transistor increases as we increase the voltage at the base. There comes a point where we get enough voltage at the base where we call it the saturation voltage, which allows all of the current to flow through the transistor. And this is the state at which we use the transistor in a computer chip. So let's take a look a little bit more in depth about what we can do with these. We use them to do what's called logic circuits, which is how the computer makes decisions. The first one that I want to talk about is the AND gate. This logic circuit, written right here, has these 3 resistors and 2 transistors. We have, since we're working with the Arduino, we have 5 volts here, and on the other side, we have 0 volts over here. We are measuring the voltage out just above this resistor, and as we said before, the voltage always drops across the resistor, so the voltage here is allowed to be higher than the voltage here. And what we're looking for is to see what the voltage is at V out. And this is a little bit more simplified version of the same circuit. We have the first transistor is here, and the second transistor is here, acting like these switches. And in order for us to get voltage to go through, we have to connect the wires, obviously. So we have to close this switch and close this switch to get voltage to run through, which is why we call this an AND gate. So if V1 and V2 are turned on, then we have 5 volts here, and since V1 is turned on, we get this wire is connected. We come here, and since V2 is also turned on, we come through here, and this point it takes a voltage of 5 volts, and we see 5 volts out here, and we drop 5 volts across this resistor. So we can read this voltage here and decide if it's on or off. If either V1 or V2 is turned off, as you can see, it opens up the circuit and doesn't allow any of the voltage to run through, and so V out is 0 volts. Conversely, we can do this OR gate, which is, I'll lift a little bit of yellow over here. Okay, So similar, I've drawn a simplified version of the circuit over here. This one is run in, here I'm going to go back over here, fit both of these in the window, I guess I can, yes. All right, back over here, this is wired in series, which means that we have to have both of them connect in order to get a complete circuit. Over here, we are wired in parallel, which means that either one of them can be turned on to complete the circuit. As you can see here, we can, if we close this switch, we'll run through this right branch to connect from the top to the bottom. And if the left switch is closed, we run through the left side. Here, this transistor is the right switch and this is the left switch. So if V1 is on, the 5 volts will run through this transistor and bring this voltage up to 5 volts at V out. Or if V2 is turned on, then it allows this 5 volts to come through and reach this point, and it's also connected to V out. And again, the 5 volts is dropped then across this resistor at the end. So we have and or gates. This is the complicated looking circuitry. Over here we just use these, what we call logic tables. So I'm going to zoom in on these. And with these logic tables, we can just represent how the circuit performs. So in the AND gate, as you can see here, both V1 and V2 have to be on. So here's the column for V1 and V2 and V out. We care about this column. This is the one that we're looking at in the computer program. We actually, or the computer circuitry, we're just looking at V out to see what it is. We measure voltage out in various places along the computer chip to determine what choices we're going to make. So in this case, we have to have V1 and V2 in order to get voltage at V out. Over here in the OR gate, the only reason that we will not have voltage out is if neither V1 nor V2 are turned on. But if either one of them or both of them are turned on, we see the voltage coming out on V out. So what does this mean? Well, we use the AND, the OR gates to make decisions in the computer. So for example, if you're holding down the shift key and you're pressing the A, for example, the computer knows that it needs to be a capital A that you're writing. Conversely, if you are typing the 1 in your 10 key, or you're typing the 1 in the numbers on the top of your computer keyboard, either one of those will result in typing the number 1 in your document. So those are two just really super basic examples of why we would use an AND or an OR circuitry. So why do you care about all of this? I forgot to mention, we're using a 1 here to note that this thing is on, or that the voltage is high, or 5 volts, and a 0 to note that it's low, or 0 volts. So we actually just use these 1s and 0s in the computer. The computer can only tell if there's voltage or if there is not voltage. That's the only thing it can do. So it's only allowed to have 2 numbers, 0 and a 1. So this is where it gets to be a little bit complicated. So we're going to go over here to our base 10 number system that we work with and talk about how we count and then how a computer counts. So looking here, we just count like this. As we increment up our 10 digits that we are working with, as I said, we have this base 10 system. We have 10 digits, 0 through 9. But when we get to here at 9, there is nothing over here. We cannot keep going. So we had to come up with a way to deal with that. And the way that we deal with it is we come over here, we carry the 1, and we carry the 1, and we start back over at 0 again. We have to have some way of knowing that we have done this operation where we have carried a 1. And the way we do it is by using these columns. So here are the columns in our number system. We have the 1s column. Where am I with my cursor? We have the 1s column here, tens, hundreds, thousands, and so on. Going the other direction from the decimal point, we have the tenths, hundredths, and then thousands carrying on the other direction. We use this decimal point here to know which side we are on. Since we have a base 10 system, we use powers of 10 in each column. And so this column is 10 to the power 0. We have 10 to the power 1, 2, 3, and so on. And negative powers of 10 going the other direction. If you aren't really familiar with powers of 10, a lot of people are not, especially with power to the 0. I've written the value of each column up here in the top column, or top row, sorry. So let's just write a number real quickly to show how this system works. So I'm going to put a 6, a 3, and a 2 here. So what is this? Well, this is 6 times 10 to the power 2 plus 3 times 10 to the power 1 plus 2 times 10 to the power 0. And 6 times 10 to the power 2 here, that is the number 600. 3 times 10 to the power 1 is 30. And 2 times 10 to the power 0 is 2. And this just equals 632. And we can just read that directly, right? You would just see this number and say, that's 632. The reason we use the base 10 system is because it's so easy to read, it's so easy to add, subtract, multiply, divide. It just is very, very conducive to working with the numbers. As you can see here, we just add a 0 every time we move up a column in this direction, and we put a 0 on the other side or move the decimal point around going the other direction. And it just makes it super easy for us to represent any number that we desire. Computers, as I said before, only have 2 digits to work with. So we are in the base 2 number system. So here we are. In our base 10 system, we can count to 9 before we run out of digits. In the base 2, we can count to 1. And here we've run out of digits, and we have to carry the 1 coming back in this direction. And look at that, we have a little smiley face. All right, happy times. So how does this work in the base 2 system? Well, first I should tell you that this system is also known, more commonly known, as binary. And that's the name that we typically use to talk about base 2. It's the binary system. So we have, similar to the base 10 system, in the base 2 system, since we have our base is 2, we have powers of 2 here. And we get rid of the decimal point, and we're just going to use these powers 2 from 0 on up. Each one of these columns, we call this a bit. And to get 8 columns, which is how many we have here, this is called a byte. So we have a bit, and 8 bits is a byte. And you know the number byte. You probably are very, very familiar with it because we talk about things in gigabytes or terabytes or megabytes. And this is just the number of bits that we use to represent the data stored in that hard drive, for example. Okay, so let's just do another example here where we write down a number. So I'm going to write down the number 1011 and show you what this is. So this is 1 times 2 to the power 3 plus 0 times 2 to the power 2 plus 1 times 2 to the power 1 plus 1 times 2 to the power 0. And if we do the math here, we can see that we have 8, 4, 2, and 1. So this is 8 plus 0 plus 2 plus 1. So we have here, we added the 8 because we had a 1 here. Did not do anything with this 4. And we add the 2 and the 1, like that. It's getting really, really messy. I'm going to erase some of this stuff. Okay, so if you add that up, 8 plus 2 plus 1 equals 11. So if we have a 1, a 0, and a 1, and a 1, this equals our number 11. In base 10, we only use 2 digits to represent this number, but in base 2, or binary, we use 4 digits to represent this number. And if we use all 8, or 1 byte, we can get to the number, so 1 byte, if we add all of these up, so just imagine I've written pluses all across there, this equals 255. That is the maximum number we can get with 1 byte of data. And just to kind of give you a little bit of an understanding here, I have written out the first 15 numbers here in binary. So if we only have 4 bits, the highest number we can count to is 15. With 8 bits, we can get all the way up to 255. And as you can imagine, we need a lot of columns to get a very big number. Where 255 only takes 3 columns in base 10, it takes 8 in binary. So why do we care about all of this? Why talk about all of this and how a computer works? It's because we have to actually store values in our program in order for it to run. So let's just look at what a program looks like, or what a computer chip looks like. So here is the processor in the Arduino, and over here we have the processor, and then over here we have the memory. Apologize for that, the cat is sneezing or something. Okay, so in the processor we do all of the math, we make all the decisions and everything, and in the memory is where we store the values that we have. Oh, excuse me. All right, so in each, whenever we have a number or some value to store in our computer to remember for the next loop we come around and we want to use it again, we have to allocate some space in memory. So we have different sizes of numbers. So we have maybe some small ones here, and maybe we have like a really large one here for this big number that we have to store some value that takes a lot of space. And as you can see, we can fill up our memory, and this becomes a problem. There's also another issue. Even if you have tons of memory space, the way that all this works is the processor has to come in here, has to read what's in this memory slot, has to go through this whole thing and look at all of it, and then it has to come back in here, it has to make decisions, do some math, whatever it's going to do, and then a lot of times it has to then come back and tell this spot what value is now stored in this spot in case the value changed. So we have this back and forth issue going on here, and it takes a lot of time if we have large numbers. So let's go back up here and look at this. Notice that I wrote all of the zeros here. I could have written zeros here, right? But we never do. That doesn't make any sense. We never ever write them because we don't care. All we want to know is what is the number. But the computer, we have to tell it how many columns it needs to look out for. If, for example, I need to store some number in the computer, and I know that number is not going to get any bigger than the number 15, but it might get close to that, I have to tell it that there are 4 columns it needs to look at. So it has to have 4 bits set aside in memory for my number, because that's how many bits are required for a number from 0 to 15. So I have to tell it, I need you to store 4 bits, regardless if they're all going to be zeros. Maybe we're storing the number 2. It doesn't really need these, but it has to have them because we may be storing a number 12, in which case we're going to use both of those. Okay, so how much memory do we really need? Well, if we want to store 1 bit, it's this little teeny box here. 1 bit is just, here's a bit, it's just a 0 or a 1. And a byte, that's 8 bits, so it's something, maybe the size of a slot in our memory. I have really, really, really straight lines there, don't I? So maybe a byte is something this big, and a byte is just going to be 8 bits, so it has to have 8 columns, and we can get larger and larger spaces, and maybe we have a humongous number that takes this space. So when you are writing your program, you have to think about the size of the number that you might need to store and what the smallest space is that you can put in memory that will be able to store that number so that you can save on processor time and also save in your memory space.